Alright, so good morning to all of you. Today we will discuss a very important concept in statistical mechanics, which is actually used in large areas of physics. It has a great range of applications from solid state physics to high energy physics. And the theorem that I am going to discuss at the end of this lecture is called as the central limit theorem. So, before I formalize central limit theorem, I would like to initiate the discussion by discussing what happens if you add two random variables and want to know how the distribution of the sum behaves like. Okay. So, we will introduce ourselves to the distribution of sum of random variables, and when the discussion matures to a stage which is appropriate to discuss central limit theorem, I shall alert all of you. Okay. So, let us start with the discussion on central limit theorem. This is the agenda of today's lecture, a very important theorem in statistical mechanics. It has applications that are widespread. Now, suppose you take two random variables x and y are two random variables and the distribution of x is p of x. So, x is distributed as p of x and y is distributed as sum q of y. Okay. So, p of x and q of y be their respective PDFs, okay, probability density functions, and now you compute a sum of these two random variables, call the sum as z, which is equal to x plus y. Okay. Simple. You take two PDFs px and q of y, you draw a random variable from px, call it as x, and you draw a random variable from distribution q, call it y, you add them up, call the sum as z, and ask a question: how or what is the PDF of z? I think the better question would be, how is z distributed? How is the random variable z distributed? Okay, that is the question I am going to answer. That is my question, and the answer is very simple. So, recall that px dx is the probability of finding x in the neighborhood, okay, in the neighborhood of or in the interval x to x plus dx, and similarly q of y dy is the probability of finding y in range y to y plus dy. So, you have to be careful here. If I am asking what is the PDF of the random variable z, which is basically answer to the question how is random variable z distributed, where it is distributed as its PDF. The answer is let us say phi of z is the PDF of z, then phi of z dz is the probability of finding z in range z to z plus dz, okay, which should tell you that you have to be careful here, that in the sense that you can't say phi of z dz is p of x q of y into dx dy. You will be tempted to say that since px dx is the probability of getting x in the interval x plus dx, qy dy is certainly the probability of getting y in the range y and y plus dy. So, phi z dz, where z is the sum of x plus y, is given as bx dx into dy dz. No, that is not true. This is not the probability of getting z in the neighborhood of z and z plus dz, for the simple reason is that while this might be the probability of getting joint probability of getting x and y, okay, in the neighborhood of x and y, I can compute the same sum by changing the values of x and y. For example, if you take z as 5, okay, this can be done by taking x as 2 and y as 3. It can also be done, it can also be obtained by taking x as 1 and y as 4. Okay. So, if I take p of p, which is a distribution of x, p of 2 and q of 3 into you know, I'll take it, I'll write this as well, this would give me the probability, joint probability of getting x in the neighborhood of 2 and y in the neighborhood of 3, which will give me the sum as 5 in the neighborhood of 5. But if I consider this p at some x1, q at y1, d at x1, d at y1, where x1 is equal to 1 and y1 equals to 4, well, this will also give me probability of getting z in the neighborhood of 5, okay, because 1 plus 4 is also 5. So, certainly what I have written here is not right, okay. So, that is why I can't just write down the probability of getting the sum in the neighborhood of z as px qy into dx dy, okay. So, this problem has to be and so there are infinite number of ways, okay, in which I can do this. So, there are infinite number of ways as x and y are continuous variables, okay. So, what I do know is that whatever probabilities I take, the sum of x plus y is constrained to be z, okay. So, how about dealing this problem slightly differently? Suppose instead of chasing the PDF directly, say I want the PDF, that is the goal of my exercise, okay. I chase the characteristic function. So, I am changing my strategy. Why? It will be clear in a short while, okay. So, let me find out the characteristic function. Now, I know that the characteristic function of the z distribution is nothing but the average value of e to the power minus I k z, okay, that is the definition of the characteristic function, yeah? And this is nothing but the average value of the complex exponential, and naturally I have to take the complex exponential in this distribution of x and y. So, I will take this as x going from x minimum to x maximum and y going from y minimum to y maximum, p of x q of y dx dy. Fine, because this is the distribution, joint distribution x and y, and I am simply weighing e raised to minus I k z in that. It is like the two dimensional Fourier transform of p x and q y. Okay, there is nothing but two dimensional Fourier transform. Now, I can write this as e to the power. So, I can separate out these integrals and write this as y going from y minimum to y maximum e to the power minus I k y q of y dy. I can do this because the random variable z was x plus y. Okay, so, I have just separated the 2 degrees of freedom into 2 separate integrals. Now, x and y are uncorrelated, so this separation was possible, and if you visualize the 2 integrals, they are individually nothing but characteristic function of the x distribution and y distribution themselves. Okay. So, this was nothing but this entire integral was nothing but characteristic function of the p distribution, and this guy is nothing but the characteristic function of the q distribution. Look at the beautiful result that we obtained. Because x and y were completely uncorrelated, the PDF of the sum has a characteristic distribution which is nothing but the product of individual characteristic distribution. So, the PDF of the characteristic distribution of, I will put a subscript here as z, it tells you that this is a characteristic function of the z distribution. This came out to be simple product of the individual characteristic functions. The subscripts x, y and z are only there to alert you that they were the characteristic functions of the respective random variable distributions. Okay, so, this is a very important result, and I am going to use this to derive the central limit theorem. Okay. So, this is very important result. Okay. So, now we are in a position to formally state and derive the central limit theorem. Okay. So, I am going to basically make the definition here or state the central limit theorem here. So, central limit theorem is a beautiful theorem, and we will come back to it many times in this course. So, I think that is the reason why I want to discuss this theorem and give it the sufficient amount of time that it truly deserves, because we will be coming back to it in the next few chapters repeatedly. Okay. Now, the theorem is very simple and very powerful. It states that if you take Let us say you sample some random variable x from an arbitrary PDF. Okay. So, you sample x from an arbitrary PDF. This PDF could be anything. It could be Gaussian, it could be exponential, it could be a Lorentz distribution, it could be a flat distribution, and so on. You could take it to be any distribution observed in nature, and you sample the random variable from this distribution. Let us say you take n variables x1, x2, x3, x4 all the way to xn. You take n random variables from this distribution p of x, okay, and you compute the sum, okay, and take the mean of this sum and call it a new variable s, okay. So, since these all of them were random in nature x1 to xi, okay, s is also random. The sum of random variables is also a random variable. Central limit theorem states that if n is very large, okay, the sum of these random variables is normally distributed. Okay. Normally means it is distributed as a Gaussian distribution. Normal distribution and Gaussian distribution are the same. The Gaussian distribution is a general distribution with an arbitrary mean and an arbitrary variance. If you take the mean to be 0 and variance to be 1, you can call it as a normal distribution or the standard normal distribution. So, I would like to rephrase this, so restate this important theorem, that if you take a large number of random variables from any distribution, does not matter whether it is Gaussian or exponential or Lorentz or flat, you add them up, the sum, if you have taken large number of such variables, will be always normally distributed, which means what? Which means the following, that if you compute the PDF of S, this will be always a Gaussian distribution. So, this PDF would be okay. So, I am going to write down the Gaussian distribution explicitly. So, P of S is nothing but, we shall see at the end of this discussion, that it is 1 upon 2 pi sigma s square e to the power minus s minus okay. So, that is the beautiful result. So, this is the P of S that I have plotted. Your P of x could be let us call this distribution of S as phi of S, okay, so that we do not use the same, okay. So, I am going to call the distribution of S as phi of S, because P is the distribution taken for x, okay. So, just to, so phi of S, which is the distribution of S, will be always normally distributed no matter what is your Px, okay. So, Px could be anything. So, let me also plot P of x, you can take any P of x,
Okay, so you could take P of x as an exponential distribution if you like. Okay, or you could take P of x as flat distribution, does not matter. Does not matter, you can take any P of x, your phi of s will be always normally distributed. Okay. Beautiful result, it does not care which PDF you take, as long as you take large number of them, the sum will be normally distributed. Now this theorem has a large number of applications in solid state physics, and as I said, in many areas of physics, whether it is fluid mechanics, turbulence, high energy physics, you have limit theorem omnipresent. And this is often the reason why you see collective behavior in systems at low temperatures, where you see long wavelength perturbations which are excited. These are the hallmark of all low temperature perturbations. Low temperature perturbations are low frequency in nature, which means you have long wavelengths, which means in each long wavelength you may have a large number of particles that are oscillating or having randomly having random motions. These particles could be on a lattice, and because these vibrations are themselves 3-dimensional random variables, in a long wavelength there are many of them. So, the fact that these large number of random variables will always be normally, the sum of these random variables will be always normally distributed, can be attributed to why you see low temperature universal scaling laws in such as heat capacity or any transport coefficient that is seen to universally behave at low temperatures. By universal I mean it does not depend on the material property, whether it is iron or aluminum or nickel, as long as the temperatures are sufficiently low, their transport coefficients will be universally behaving with some scaling law. So, in some sense the implications of central limit theorem are very deep. So, let us formalize all that with some very simple mathematics. So, what I am going to do now is that define this random variable, it is already defined here. So, let us call this as equation 1. Okay. So, if I want to write down a characteristic function of this random variable distribution, so remember what we want is the following. We want phi of z, phi of s, our sum is now s, okay. We want phi of s, okay, but we will start with the characteristic function, okay. Right. So, now the characteristic function can be written as these n integrals. I am not writing the limits here because the limits are understood, they are from the low value to the x lower to the x maximum. So, I am not writing it, but you should understand that these integrals are all definite integrals, and you will say p of x1 into p of x2 up to p of xn d of e to the power minus I k s d of x1 d of x2 all the way to d of xn, okay. And this can be written as phi of k as all these n integrals p of x1 up to p of xn, and I can write down this variable s as x1 plus x2 all the way to xn divided by n into dx1 all the way to dxn. Okay. And since these variables are uncorrelated, I can split up these exponentials and write them as e to the power minus ik x1 p of x1 into e raised to minus ik x2 p of x2 dx2 all the way to e raised to minus ik xn p of xn into d of xn. Okay. So, if you look at these definite integrals, each one of them is from x1 minimum to x1 maximum. Okay. Similarly, this is from x2 minimum to x2 maximum, and this is also from x3 minimum to x3 maximum. So, if you look at these definite integrals, they are all the same because the integration variable is dummy. Okay. The integration variable in a definite integral is dummy. So, this is like integral e raised to minus I k x by n into p of x dx whole raised to power n, because there are n such integrals. Okay. Because the integration variable is dummy. Fine. Now, look at this. This integral is nothing but, should remind you immediately that this integral is nothing but the definition of the characteristic function of my PDF, except for the fact that this is the characteristic function evaluated at the wave number k by n. So, this is the characteristic function of my PDF taken at k by n, and the entire thing is to the raised to the power n. Okay. Now, if you recall the definition of the characteristic function from the past few lectures, it is nothing but a summation some j going from 0 to infinity minus I k by n to the power j jth moment divided by jth factorial. Okay. That is the characteristic function for the wave number k by n, and the entire thing is raised to the power n. Okay. Now, you can write down this summation for a few values. Okay. So, you can write it for a few values, as for, let us say, if we write for j equal to 0, 1 and 2. For j equal to 0, you simply have 1. For j equal to 1, you have minus of ik by n mod x, and for j equal to 2, you will have into second moment by 2, plus the third term that you have is basically of the order 1 by n cube. The entire thing is raised to the power n. Okay. So, now recall that our assumption was we had taken n to be much larger. That was the assumption. Okay. We are going to derive the central limit theorem for very large n. If that is the case, I can drop the terms of the order n cube 1 upon n cube in comparison to 1 by n square and 1 by n. Okay. So, when you drop this, you get the characteristic function as 1 plus minus I k by n into mod x, and the second term I will write it as minus k square by 2 n square into mod of x square whole raised to n. Fine. Now, you visualize this, some of these two terms as some variable r. So, what you have is basically so this is basically 1 plus r to the power n, okay, because I visualize the sum of these two terms as r. Now, the expansion of 1 plus r to the power n is just e to the power n r if n is much larger than 1. Okay. So, this is an approximation that 1 plus r to the power n is e raised to n r. Now, simply put r as what I have written here. So, this becomes approximately e raised to n times r, which would be just minus I k into mod x minus k square by 2 n into mod x square. Okay. Just multiply n to r and raise it to power e. Okay. So, this is our characteristic function. Now, what you are looking here is just a Gaussian characteristic function. You know that that Fourier transform of a Gaussian is also a Gaussian. Is also a Gaussian. So, in some sense our theorem is already proved. If I want to compute the PDF phi of s, this will also be a Gaussian distribution. Okay, it will also be a Gaussian distribution. So, my theorem stands proved as is. Okay. But if you want to prove, if you are the guy who is not convinced, in fact, you can match your expressions in the discussion on Gaussian distribution. We got precisely this expression for the Fourier transform of the Gaussian distribution. So, you know that the inverse Fourier transform of this would be a Gaussian distribution. But if you want to see explicitly how this is possible, well, you can do that also. Okay, so explicitly you can show that this is phi of s. So, remember I wrote down this expression without solving, but you can also get it by doing a Fourier transform. So, let us do that. So, you can write down phi of s as the inverse Fourier transform of phi of k. The inverse Fourier transform is nothing but k going from minus infinity to plus infinity e to the power I k s phi of k dk. Okay, you should get that. So, let us do it. So, you have 1 upon 2 pi k going from minus infinity to plus infinity e to the power I k s, and phi of k is just derived here. I am going to just write it here and just copy it from here. into dk. Okay. Just need some manipulations here, which are very simple. So you write this again as minus infinity to plus infinity, and you can see that this is easily written as e raised to minus ik into mod x minus s. So I have taken the first two exponentials as is, a is to minus k square by 2n to mod x square d of k. Okay, and these are very simple integrals. So you can perform construct a perfect square in the numerator. That is always the trick to solve these Gaussian integrals. So the perfect square that I am going to construct is on k square. So I am going to take the prefactor here as minus mod x square over 2n, and I am going to write it as k minus so the k square term will give me a second term here, twice of ik with a minus sign becomes minus 2ik, and I have a 2 here outside, so it gets cancelled off, but I need an n here because I had to cancel the n here. So 2 times of this would give me just ik into mod x minus s with a minus sign it becomes, and I also need a division by mod x square. So that cancels with the outside mod x square, and 2 cancels with 2, n cancels with n, I get this. Okay, now there is a quadratic term which will come extra, and that would be just the entire thing square, but it has a I square that cancels off with minus 1 I square, so I get a plus sign, so it is a minus sign, mod x minus s the whole square, n square by n is n, and I will have divided by just mod x square by 2. Okay. So the quadratic term would be n square cancels with n, that gives me an n here, I square becomes minus 1, and I will have an x square, the denominator, yeah, so that is it. Okay. Right, so you can check this. I have computed this as the factorization, and now you can see you can substitute k plus mod x minus s into in. This is a constant. Okay, so this is basically okay, so this is my variable is k, so the entire thing here is substituted as some u. So d of k will be just d of u because the entire thing is just a constant, is just a constant. Okay, so my integration above will become 1 upon 2 pi into u going from minus infinity to plus infinity e raised to minus mod x square by 2n into u into e raised to minus mod x minus s the whole square by n divided by 2 into mod x square dk. This exactly is a constant. Okay, so for this integral, this is also a constant. It does not depend on k, so it will come out of this. So what I'll have is basically e raised to minus, and I can write down mod x minus s the whole square as s minus mod x the whole square. Okay, square of a negative number is the same as the square of the positive number. Okay, so I can write this as s minus mod x the whole square, okay, divided by 2 into x square by n. Fine, and this is multiplied by 1 upon 2 pi, and the integral is going from minus infinity to plus infinity e raised to minus x square into u by 2n d of u. This is a du, okay, this is not dk, this is d of u. We have converted the k integral into u, and you know the Gaussian integral, which is square root of pi by a. So you write this as e raised to minus s minus mod of x the whole square divided by 2 times into 1 upon 2 pi into square root of pi by a. Now a here is x square by 2n, so this would be just x square by 2n okay. So this would just be, if I write it as 1 upon square root of 2 pi okay into e raised to minus s minus mod x the whole square divided by 2 times x square by n okay. And if you see the way we have defined our variable s is nothing but all the summations of x divided by n. So if you recall that s itself was summation of xi by n. So if I take a mod on both sides, okay, so this is nothing but this is already nothing but mod of x, okay, that is the average value of x, because summation xi by n is mod of x. So I can rewrite this as phi of s as 1 upon square root of 2 pi x square mod divided by n into e raised to minus s minus mod s the whole square divided by 2 times x square mod by n. Okay. Now, if you compare this with the definition of a standard Gaussian distribution, comparing this with standard Gaussian distribution, or standard normal distribution. Okay. You can see that the variance of the S distribution is nothing but the second moment of the random variables that were drawn from P of x divided by n, and the mean of this was just nothing but the mean of the variables themselves. Okay. So, this proves your result that the distribution itself, okay, is normally distributed. So, the take home message here is, when I look at this expression, okay, that I am going to sort of box it, is that my distribution of S is also normally distributed. Okay. So, this is the take home message of our discussion. So, S is normally distributed. Okay. So, this is the end of this proves the central limit theorem, and that is the proof of a very important distribution that we started off at the beginning of this lecture. Okay. So, we end the discussion here. In the next class, we will talk about many random variables and the concept of conditional